All right, let's start. I'm Edouard Oudet. We'll talk about very minimal surfaces and symmetries.
Yes, so I changed a little bit the title, but anyway, the subject is the one you all know. So before to start, I would like to thank the organizer for this great organization. It's such a pleasure to be here. And just to have an idea of the audience, I wanted to know how many people are somehow involved in numerical analysis or scientific computing. Perhaps not so much. I expect not so much, but perhaps some of them. Okay. Okay. Usually, when I give a talk, most of the people are more on the scientific computing side, and so I spend a lot of time explaining difficult geometry, at least difficult for me, which could look a little bit straightforward for you. So anyway, so this is a long story, and I would like just to summarize which are the big steps we made in the last 6 or even 7 years with my collaborators. So we started the story with Shuyan and Braxton Hosting, who gave a talk several weeks ago, I think, on a similar subject, but I will underline the differences. And in the last 2 years, we proceed and we focus on the extension of all what we did in any genus, essentially. I will not have with Michael now. I will not have the time to explain all the details of these recent parts, but I would like to focus on the symmetric question, which is somehow relatively new, at least from the computational point of view. Okay, so I will not insist on what is a free minimal surface. So this is my usual introduction. So up to now, if you ask ChatGPT, the result is not completely satisfactory. So it has something to do with the minimal surface. So you all know what is a minimal surface. And the boundary has to be inscribed in the ball, for instance, or in a sphere. In the sphere, excuse me. So there is a lot of work in that direction, and we discovered a small part of this work, as I told you, something like 7 years ago, together with Shuyan and Braxton for a long stay in Taipei. And unfortunately, we were alone in the sense that it was research in pairs, in triple, and so no geometer, no remaining people around. So we have to try to understand by yourself what is exactly the situation and what is known on the subject. So we started by studying so I do not remind you. So this is the explanation of what is Steklov eigenvalue problem. I do not insist on this. Perhaps just on the fact that, as you all know, it is based on harmonic function. You are looking at harmonic function on the surface. You have a surface with boundary, and the eigenvalue problem is on the boundary of the surface. You have a sequence of eigenvalue, blah, 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 blah. This is very, very, very classical, and you are all experts of this. And the starting point of this story for us was the paper of Fraser and Shun in 2015. I know that there is a lot of work around, but at least this is the paper we try to understand in details, at least from our point of views. And so I remind you the result, but I'm sure most of you have the result in mind. At least, so originally it was for maximizing the first eigenvalue, Steklov eigenvalue in genus 0. Whatever the number of boundary components, if I remember well. And the question is, what happens if you maximize this product, which is the Steklov eigenvalue number G, time the length with respect to the metric. And so you maximize with respect to the metric on the surface. So this product is invariant by Motessier, but by scaling, let's say. And what happens is this miracle, at least when we read these results, we didn't understand exactly why, or what perhaps is very natural for you, but I will try to give you some intuition, at least from the shape optimization point of view. So if you consider the optimal metric, then you end up with an eigenspace, which is of dimension 3. So this is the first miracle for us. And additionally, you have the fact that you can identify a triple of eigenfunctions in this eigenspace, which gives you a parametrization of free minimal surface in the sphere. Okay, so that's the results you all know, and there is a lot of extension of these results in other genus with other techniques. And I think that the main goal of the paper, if I remember well, was to prove actually the existence of such objects by proving that the optimization problem, the Steklov optimization problem, has a maximizer. So this was the motivation, and it's very technical at least, and I think there was some technical point that have been to discuss anyway. So this is the results. And of course, you all know two very basic examples of free minimal surface in the sphere, in the ball, which are the flat disk and the catenoid, the critical catenoid.
Excuse me, you are maximizing with respect to G and sigma.
No, excuse me, so I was not clear. No, the index of the eigenvalue is fixed. So let's assume that is the first one, the first non-trivial one.
So you're maximizing with respect to the metric
exactly,
given sigma, or also
sigma is the eigenvalue. The surface.
Capital sigma, the surface. Can the surface
evolve?
The
surface is fixed.
Is fixed, but you let all the rest of the metric.
Yes, and what is very important in that story is the fact that you maximize among all the metrics, not only in the conformal class. You really.
But the capital sigma is fixed.
The surface is fixed. Yes. Yeah. And this surface fixed and actually fixed the number of boundary components. Okay, so
fixed, but the metric.
Yes, and consider so the picture that I have in mind.
Yeah, the topology is fixed.
Yes, exactly. The topology is fixed. Yes, exactly. The number of boundary components is fixed, and then you maximize the metric on this set. Okay. Okay, so you have these two examples. And actually, it's not clear, and it was not clear that other such surfaces exist. And several authors try to describe numerically, and I will tell a word about the other approaches in several slides, try to approximate these objects. And here our goal was really, because we are from the shape optimization community, so our goal was really to maximize the eigenvalue and use this strange phenomena that you can find a parameterization in the eigenspace and produce some parameterization of these strange minimal surfaces. Okay, so this was the goal, which is very common. And just a few words about the optimality conditions. So as I told you, it's an optimality with respect to the metric. So for me, a metric is a matrix field. Non-negative definite matrix field. And so if you optimize with respect to the conformal factor, so this is relatively usual for people who optimize eigenvalues among volume measure constraints. So if you minimize Dirichlet eigenvalue under some constraints, then you end up that if the eigenvalue is optimal, then you have some notion of generalized derivative, which tells you that something like the subgradient is proportional to the gradient of the constraints, essentially. And so here, just by the optimality with respect to the conformal factor, so you just change the scaling of the matrices, you obtain the sphere condition, okay? So it means that that's not very, you see, you are very far from having a minimal surface. Huh? You just know that the boundary is inscribed in the sphere. And now in order to have a conformal mapping, then you have to optimize among all the conformal classes. And then you have that the mapping, of course, since you are dealing with harmonic functions, the vector is always harmonic. But then you will have a conformal mapping only if you optimize among conformal classes, okay? So I think this is the way we translated it in a way we were accustomed to see this kind of optimality condition, but at least for us, the first condition is just an optimality condition for the non-smooth problem. So the non-smooth part comes from the fact that you are maximizing an eigenvalue, and for the maximal situation, at the maximizer, you know that the multiplicity is 3, and you know that the functional is not differentiable in this case, and so the derivative is more complex than the one you know, than the one you expected. Okay. So this is the first remark. And now we wanted to parameterize the conformal classes. So we discussed a little bit, so it looks very, so now I'm diving into the numerical parts, but I will stay relatively far away from the details. I just want to describe how we parameterize the problem, okay? So the way we parameterize the problem was to be able to parameterize all the conformal classes. So as we said, the topology is fixed, and then I would like to change all the metrics. So of course, if you're going to work with the matrix field, it's very constrained, because then you will have some kind of point-wise constraints, because if you just define your unknowns to be a matrix field, which is the matrix field which represents a metric, then you have to assume that the metric is non-degenerate everywhere, in all your points, in all your domains. So that's very, very strong. You will end up with an optimization problem with point-wide constraints, which is very difficult to manage, okay? So the idea is to change a little bit the problem, and what is very attractive in that problem is the fact that you can work only on the boundary. So how you can do that? You can do that because you can assume that actually your surface is conformal to a disk minus some small disk inscribed into that unit disk. So you fix the unit disk. You want a surface with, let's say, like two boundary components. So, because I would like to recover, for instance, the critical catenoid. So the way we do that is just that we consider the disk, okay, and we would like to find a parametrization. So the way we want to describe our surface is by describing all the conformal classes, and I can do that by considering the disk with some circular hole. So it means that here the exterior disk is fixed, and the interior disk, which is a hole, actually, changing this hole, the position and the radius of the hole change the conformal class. So it corresponds to change the ratio of the eigenvalues of the matrix fields, okay? So this is a result, and so of course you can do that if you are interested in recovering a surface with two boundary components like the catenoid, and if you want to play with something with more boundary component, then you will increase the number of holes. So let me say that, and we have a proof for that, because you have a lot of results in conformal mapping. But this one was not obvious, and it was not easy for us to find this result in the literature. You can parameterize all conformal classes with surface with boundary, with the disk with circular holes, okay? So genius, I'm talking about the genius 0 case. Huh? And so by doing that, now look at what happens to the PDE. Now, if I'm looking at optimizing the conformal class, now I am in a flat surface. And I see that the effect of the, so I do not want to enter into the details, but this is relatively standard. If you change the metric, if you change the conformal class, then you will see that you will have the effect of the conformal factor which will appear in the eigenvalue problem. So now it means that, to summarize, it means that my unknowns are, and I will summarize this a little bit later. So let's say the center of the disk in the one-hole case, its radius, and then some density, which is defined in the so in this circle. And I do not have to care about the density inside. Okay, the eigenvalue problem is defined on the boundary, and of course, this density plays a role, at least the conformal mapping plays a role when you look at the Laplacian, but we will discuss this a little bit further, okay? So this is the parameters of my eigenvalue problem. And I may expect some singular behavior. If I change the topology, I may expect at some point that, for instance, if the two interior disks are very small, I may expect that the density blows up. And so it means that from the numerical point of view, we have to be very, very precise. So at this point, believe me, if you are not experts, it means that something like naive finite elements methods are not enough precise to describe the solution I'm interested in. Why? Because I have to describe the solution of a PDE, but this solution has to be related to an optimality condition of a non-smooth problem. And these two facts, the fact that I'm looking at the solution of a PDE with a non-smooth problem, makes it very, very tricky from the numerical point of view. And standard finite element methods are not enough. Okay, so this is why you have perhaps seen a talk of Braxton Hosting in the last months. So he focused on a boundary method, boundary integral method, which is very precise in order to describe the solution of genus 1 PDE problems. And so I will do exactly the same with another approach, which is perhaps more naive, but which is easier to extend in higher genus. Okay, so as I told you, this is now my parameterized problem. So I want to maximize some products, so assume J is equal to 1, of the measure of the boundary. Of course, I have to impose that my all disks have to be inscribed in my original disk, the unit disk, let's say. They do not have to intersect, but this is a very small number of inequalities. And I have to assume that the density, which is also one of my unknown, and actually the crucial part of the unknown, has to be non-negative. And this is the problem I would like to maximize, okay? Now, how can I do that? Okay, I can compute optimality condition. And so this is, as I told you, this is the result of the first order optimality condition just with respect to the conformal factor and with respect to some data which involve the conformal class. I obtain something which is more tricky and which actually gives you the fact that the mapping at the end is conformal. Okay, so now this is some perturbation theory which explains the computation of the derivative. I go through that. And now I would like to explain the numerical method, because it's a numerical method which is very, very simple, without any meshing, without any techniques. You just have to understand harmonic functions. And actually, I didn't know, perhaps you're expert also of that, but I didn't know that harmonic functions can be very tricky. So we all know that in the complex plane, when you have a domain which is simply connected, any harmonic function is the real part of some analytic function, okay? Okay, so if I have a domain without any holes, then, and if I'm interested in looking at harmonic function in that domain, so what I can do is just to look at functions which are real part of any analytic function, okay? So from the discretization point of view, this is very, very nice, very simple, because then there is a discretization which is very natural, which is just, excuse me, the discretization considering some monomials, okay? So what you can do is just consider, for instance, the sequence as a Galerkin basis. You can consider the real parts of all the z to the power k for some k which is equal to 0 to n. So this is space of function. You consider this space of function, the vector space mapped by these functions. And of course, you also have to consider the imaginary parts. And then the closure of this space will be exactly the harmonic functions, okay? In the simply connected sets. And now you have an extension to this, which is what I call logarithmic conjugation theorem, which is a little bit, I don't know. So that's a big name for something which is not so evolved, which says that now if you have holes, you have to add two components. So you have to consider these functions, but you also have to add, so let's now consider a domain with one hole or with two holes. So this space is not enough. The closure of this space will not give you all the harmonic functions. So the ones which are missing are the logarithmic poles, okay, and the meromorphic parts, okay. So what you have to do now to define a complete discretization is to consider some points which are, so you fix points inside of your holes. And now you consider the z minus ai to the power minus k. So the imaginary part and the real part of this function have to be added to the list. And you also have to add, so you have a sequence for every pole, okay? And you also have to add logarithmic singularities. So that's very natural. Okay, and now if you do that, you are able to approximate Steklov eigenvalue problems in this configuration very, very efficiently. What I mean by very efficiently, I mean up to 16 numbers. Okay, so up to machine precision. And this is not possible to do that with standard finite element methods. Okay, so let me show you an example of the method. So this is the proof of the logarithmic conjugation theorem, which is actually just containing Durham theory, actually. So now let me show you the numerical approach. So this is the problem I want to solve. And how can so I just explained how to define some space of functions, some Galerkin space, which makes me possible to approximate harmonic functions, okay? So now I didn't tell you how I can solve my eigenvalue problem, okay? So now it's relatively simple because imagine you have a function which is in that space, okay? So you want to find a linear combination of all these functions which solve your eigenvalue problem. And so the way you will do that is just in the least square sense. So you will just sample the boundary. You will just sample the boundary points. And then you will impose this condition all along the red points by least square. Okay, so this is very, very simple. I mean, it's a third-year exercise to compute Steklov eigenvalues in that way. You do not need any mesh, I insist. And at the end, you have a machine precision result. Okay. So with that trick, of course, so the price to pay is to be able to provide this basis of harmonic function. I mean, I forgot about the PDE because I knew the solution, which is in that case very, very simple. I'm just looking at harmonic functions, okay? But with this huge advantage of knowing the solutions of my PDE, I am something which is very, very simple to implement, okay? So now how to assemble this condition. So I sampled the evaluation of my linear sequence of functions in my eigenspace. And at the end, I have to solve some generalized eigenvalue problem of that kind, which is not symmetric, but you can symmetrize it. And then you can show that you have a spectral convergence solving this generalized eigenvalue problem. Okay, so perhaps one example in a very, very naive setting. So here, the density, if I remember well, so remember that there is a row somewhere, huh? But the row is involved in the matrices I just described. And so here, this is the description of the approximation in logarithmic error. And you see that with an m, so the m here is equal to n here, more or less. So with something like 32 terms plus the logarithmic terms, I'm able to have a convergence to the scale, to the logarithmic scale of -16, okay, which is the machine precision. I cannot go further. So these matrices actually are very, very small. Huh? They are dense. That's the problem. They are dense, but they are very small. Okay, so the end of that part is that in genus zero case, so here I'm still discussing the genus zero case, I'm able to compute very efficiently Steklov spectrum of these flat domains. And if I have a density rho, it doesn't change really the problem, and it doesn't change the spectral convergence. Okay, so now you know most of the story. So again, from the numerical point of view, it's not so trivial, but let me show you now the results. Perhaps you perhaps Braxton showed you this part of the results. So what we obtained 4 years ago was this sequence of holes in the disk. So here, this is the optimization of this disk. So we obtained this central position. And of course, associated to this central position, we obtained the critical catenoid. Okay, this guy is a new guy, which is the result of something which is relatively symmetric. So here I put the center of the disk with the I point the center of the disk with the red cross. And here you see all the configuration, increasing the number of boundary components. Again, it is still in genus zero. Okay, and how the surfaces look like. So this is a very, naive drawing of our first results obtained 5 years ago. And so we see that the number of holes, the number of boundary components seems to be spread homogeneously somehow in the sphere. And this is a result that has been proved by Jean and Alexandre in a very nice paper, which is an homogenization results, and which is illustrated a little bit by these results. Okay, so this is what we obtained. And at this point, I have to quote Mario, who produced some wonderful simulation about exactly on that subject. And it was even possible for him to impose some symmetries. My only remark to try to save what we did is that he's working on mesh refinement, on mesh optimization using BRAC software. And so he's not using the spectral representation, okay? So it's a very, very nice job. If you didn't already, but I'm sure most of you have a look to his web page. Have a look to his results. It's very impressive. And with his approach, he's able to describe with meshes such objects. So what are the differences? Again, another tentative to try to save our work. So he's not using the spectral information. So he doesn't know what is the multiplicity of such or such objects. Okay. Another perhaps more interesting point is the fact that at the end of all this machinery I try to describe, it's the fact that we have an analytic parameterization of these objects. In the sense that at the end, we have real functions. So these are functions. They are not piecewise linear functions. We have functions on the domain. So we have a domain which maps with real function a surface, which means that we are able with this function to compute curvature and compute the normal, but analytically. Once the coefficient in front of these guys are given, are computed, we can compute everything analytically, okay? The only approximation are the coefficient in front of the basis. But once we have that, we do not need approximation to evaluate the curvature, stuff like that. Again, it is something which is completely analytic, okay? And so, which means that a posteriori, we are able to evaluate the quality of what we obtained, and we obtained mean curvature, again, up to 10 minus 10 digits. So, which is very far from what you can get with the mesh evolution. Okay, so this is very something different if you are really obsessed by precision. Again, I try to find an excuse to continue that job. Okay, so have a look to Mario work, which is amazing. And now I would like to say a few words on the Genius 1 case. Okay, so as I told you, the difficulty is to identify the right sequence of harmonic functions. So what are the troubles in that case? So for instance, considering Genius, so you all know that every Genius 1 surface is conformally equivalent to a flat torus, one of the flat tori. And so it's also true with holes. I mean, you just have to choose one flat torus and then optimize the position of the holes, okay? But you have to change also the class of the torus. Huh? You have to change the class of the torus, the position of the holes, and then the densities. So it's the same job, but the problem is that you do not know I didn't know what are the harmonic functions on the flat torus, okay? And so perhaps you know that, and so so here I'm considering a flat torus associated to a lattice omega 1, omega 2, and I'm interested in functions which are doubly periodic. So if you look, of course, at holomorphic functions, so here I consider holomorphic function, analytic functions. So analytic function on the torus, they are very few, or you only have the constant because they are bounded, okay, obviously. So you have to consider only meromorphic functions. So now meromorphic function, we all know that it's a big subject to look at meromorphic functions on surfaces. And now the question is, how can we compute these guys? Do they exist? Do they exist of any order? So what is a complete family? That's the question. So there is one very famous function, perhaps you heard about, which is Weierstrass function. So this function is associated to that lattice, excuse me. So omega is a combination of the omega 1, omega 2. So let's consider one direction which is equal to 1 and the other is free, is omega. So then this function actually, by definition, because you are summing on the lattice, is summable. So that's the miracle, is summable. So of course it will be doubly periodic and is meromorphic and has a pole of order 2 in the middle. Okay? So now the question is, can we, okay, let me go back and try to mimic what we did in Genius 0 case. So as I told you, I cannot expect to recover these guys. So these guys are holomorphic. Here, the only holomorphic function in the torus is the constant. So this one doesn't exist. So now I would like to recover the real part and imaginary part of some Laurent term. so which are meromorphic function of order 1 to minus plus infinity, and the logarithmic terms, okay? So I understand that this one will play the role of 1 over z2 by definition, okay? So I'm very happy because now if I, so some, you can, a lot of analytic rules, a lot of algebraic relations are known about this Weierstrass function. And the one I used is this one and this one, which tells you that if you differentiate, then, excuse me, you are able to differentiate just by the evaluation of that function, okay? So it means that if I want to have a pole of order 3, I just have to differentiate once, okay? But I do not want to differentiate that expression. So but I'm able to use this relation, these two relations, these three relations, and which tells me that, okay, just by evaluation of that function, recursively, I am able to evaluate all the derivative of Weierstrass function. So we are very happy because it means that we are all this guy starting from k greater or equal to 2. Okay? Just by differentiation and using what people did on special functions. So I have almost all the family, but some guys are missing. We do not have the order 1, and we do not have yet the logarithmic terms. If you have any question, do not hesitate. Okay, so pk, so the k derivative plays the role of this one. And so there is so of course you can integrate term by term. So you have a series, you can integrate it. And so you obtain this term, and so you have to arrange a little bit the term to preserve the convergence. And then doing that, you obtain a pole of order 1. So we are very close to have a complete family, but there is, okay, there is a minus just for the game. But still, we have a pole of order 1. The problem is that this function is not doubly periodic. And actually, you cannot have a meromorphic function which is doubly periodic of order 1. Okay, but it satisfies some quasi-periodic conditions, which are these conditions, which are a little bit weird. And these conditions tells you that if you consider that meromorphic function, you perturb it by some analytic constant which are known times z, minus z conjugates some other constant, then this function will be doubly periodic. So this was the surprise for me because I didn't pay too much attention to my complex analysis course when I was young. And so I forgot that. So this function is not doubly periodic, but you can make some correction. But be careful, you are not anymore analytic, meromorphic. Okay? And you have to have these 2 degrees of freedoms in order to correct the 2 quasi-periodic modes. And then you end up with this. What is very nice is that this one is doubly periodic, and its real and imaginary parts are still harmonic, of course. So you have poles of order 1 which are harmonic. And so based on that, you have almost all the family. Did you follow me? Okay. So this was known, and this is not due to us. But with these tools, we have the order 1. Okay, and now a little bit more involved. There is some function which are the logarithmic version of for flat Tori. I do not want to insist, but again, it's a question of logarithmic derivative. So you compute the logarithmic antiderivative of given zeta, and then you end up with a function again, which is called the logarithm of the modulus of sigma hat, which has constant Laplacian, so doesn't have a 0 Laplacian, which comes from this function. So again, it's the same trick. The idea is that taking an antiderivative, you do not preserve doubly periodicity. Okay. So what you can do, what you can preserve, is that the Laplacian is constant. So it means that you may have some poles, but pairs of poles of order 1 and of logarithmic term, you may have a pole of plus logarithm in one point and minus the logarithm in the other point. And so at the end, it will give you a function which has a constant Laplacian. Okay, so what we were able to prove at the end, because I would like to show you now surfaces at the end. So do you remember the families we had, which was the morphic part, the logarithmic part? Now the complete family is this one. So if you want to have a complete family of harmonic function, you have to consider the constants, the holomorphic parts, the meromorphic parts coming from the Weierstrass function and its derivatives, the logarithmic terms coming from this magic log sigma hat function, and the sigma hat, which is the correction of the zeta hat function, which is the correction of the zeta function, which is doubly periodic. And with all these terms, you may have something which is harmonic. Be careful. As I told you, this one has constant Laplacian. The Laplacian is constant, but is not 0. So we'll have to force that the sum of all these coefficients is equal to 0. As I told you, you will have something like plus logarithm at one side and minus logarithm on the other side. And so the sum will give you something with the constant Laplacian equal to 0. But this is a new fact for me, at least. So what are the unknowns when you solve a Steklov eigenvalue problem on a flat domain? The unknowns are these coefficients plus these coefficients under the constraint that they sum to 0. Okay, so exactly. If you have only one hole, you do not have that. And you can obtain that result just by the residue theorem.
Which theorem?
Residue theorem. If you count the number of poles and integrating along the boundary of the flat domain. Okay, so now the idea, the global picture is the same. I have the sampling, I have my basis, I'm able to compute my spectrum. And now I'm able no, I will not optimize right now. I would just want to show you the precision. So this is the flat domain, the square torus. And again, this is the precision, and here we obtain a precision up to 10 minus 100, okay, in multi-precision, okay. And so here you have a solution of some, so this is not Steklov problem, this is the analogous problem, which is the harmonic extension problem. With a given f, I try to find u which extends f, okay. And this is the precision we obtained. And as with this function, using these special functions, we were able to implement something which is very, very precise. Okay, and so this is the result of this is some Steklov eigenfunction, excuse me. And this is okay, so we have a posteriori estimates, so we are able to provide rigorous estimate of the results, which was something obtained by Benjamin Bogozel. And this is the kind of precision we have, just to have a picture in mind. Okay, so this is the eigenvalue of these domains with constant densities, and all these numbers are exact. Okay. Okay, so now we are able to provide some tools to compute the spectrum for a genus 1 surface. So I do not have the time to show you how we optimize the surfaces. I just want to show you the results. So this is so I'm cheating. You only have two kinds of surfaces on this drawing. Okay, so you just have, so they are all of genus 1, and you have 1 or 2 boundary components. Because I know that Braxton show you 1 boundary component, so I wanted to show you 2 boundary components. Okay, so these are the surface, and this surface, so I told you that there is no mesh in my story. There is no mesh, but this is just a mesh to represent the surface, okay? To obtain the description of these objects, I use analytic function provided by analytic sequences, okay? And again, this object, the one I show you, have mean curvature up to 10⁻⁻⁻, okay? So we are able to provide a very precise solution of the Steklov problem, but also of the optimization results, really taking care of the non-smooth optimality condition. And of course, if you look at the Gaussian curvature, okay, you know that the Gaussian curvature is not minimized. It's far from being equal to 0. Okay, so now so I just want to take you 5 minutes. I want to explain, so this is the surfaces we obtained in genus 0, and now the ultimate approach. So the ultimate approach is something which is very nice, and perhaps from the theoretical point of view, it may be useful. I don't know. So with Michael, we ask ourselves so we did 2 things. First, we extend all this machinery in genus greater than 1. So this is a little bit technical, using 1 forms and so on. But this is very technical. But we were able to do exactly what I show you on genus 1 with genus 2, genus 3 surfaces. So now what we wanted to do, because Mario was really far away from us in front with his minimal surfaces, and we wanted to impose symmetries. Is it possible to impose symmetries? And this is a little from the numerical point of view. When we compute the surfaces, is it possible in advance to impose symmetries? So there is this wonderful article of Karpukhin and his colleagues, which says, okay, if you optimize some eigenvalue, some Steklov eigenvalue, then in genus greater than 0, you may find some eigenspace which has a dimension which could be higher than 3, okay? I'm not from the Riemannian geometry community. I'm essentially interested in surfaces in the Euclidean R3 ball, okay? So I'm interested in real 2-dimensional objects. And so what Karpukhin and his co-authors propose is to prove the existence again, is to impose some symmetries on the problems. When you essentially, my translation is when you have an eigenspace at the end of the day which has a dimension which is too high, impose some symmetries, and luckily you will end up with a dimension 3 eigenspace. Okay. Okay, so that's nice, but that's very nice because if you optimize the first eigenvalue, for instance, of Steklov in the flat torus, in the flat tori, you will find an eigenvalue, an eigenspace, excuse me, of dimension 4, not of a dimension 3. If you want to recover the surfaces I just showed you, you have to prescribe some symmetries. So this is what we did from this. This is kind of amazing. We did that numerically. And actually, it is the key from the theoretical point of view. Of course, it is far deeper than what we did. But anyway, this is what the ideas are relatively similar. So the question is now, how can we impose some symmetries on the surfaces? And so the idea is to change Steklov eigenvalue problem into a vectorial Steklov eigenvalue problem. So instead of looking for one eigenfunction, instead of looking for the eigenspace and look for 3 eigenfunctions in the eigenspace, we will look for all the 3 eigenfunctions in the same time. Okay? So what we're going to do, so we want to impose so we'll fix some group action on the surface, and we would like to preserve this group action in order to force some symmetries. So what does it mean? It means that I have some parametrization, and now I will look for a triple of eigenfunctions which satisfy these relations, which tells you if I apply my action on my variable in my parametrization space, I want to see the action, the rigid movement of this action on the triple of eigenfunctions. Okay? This tells you exactly that you want to have some symmetries in the parametrization space that you want to see on the sphere. Okay? So this is a constraint that you can impose because you just have to consider in your basis, you just have to fix your group. Of course, your group of symmetry is fixed. And you can consider your triple of eigenfunction and compose by the action of all, by the mean of the action on all your group. Okay? And so if you do that, you take your sequence of eigenfunctions, you copy these sequences 3 times, then you take the means with respect to your group action, and at the end, you have a vectorial space which satisfies exactly your symmetric condition. And luckily, you may have a solution, an eigenvalue, which is optimal and which jumps from a multiplicity 3 to a multiplicity 1. But you do not care because at the end, you just want one triple. And that's a kind of magic because then you can use all the standard tools of differentiability, of functionality, and that's really, really simpler. Okay, so this is the very naive Steklov eigenvalue problem. And using that, we were able to impose some symmetries. So let me show you, first I will show you the 3 different cases before to conclude. So we were able to recover the catenoid, nice, imposing the symmetries. That's something a little bit different. And then, like Mario, we wanted to impose some tetrahedral symmetries. And so what is very cool is the fact that in that game, at the end, once you know the density on one of the circles, so here, if I know the density, you remember I have densities on my holes. So if I know the density on the green part and on the orange part, using the symmetry, I know the densities. Okay, so one is missing here. So I know the density everywhere. So it means that I can restrict my computation on just on 2 holes, even I have a great number of holes. That's very cool from the numerical point of view. And here, you have the mesh of all the parametrization space of that symmetrization group. And again, you will see that the problem is just the unknown are just located on 2 of the circles. The same for the symmetry of the cube. Again, you have your conformal space, and you have your unknown, which are just here. And knowing the values here and here, you know all the values here. So now how are the surface? How do they look like? So this is the surface associated to the cube symmetries. So you see, so again, this is a minimal surface. So this point is the point at infinity. But again, this is just a way to represent the surface. So this surface is represented by this mesh, but we have some analytic parametrization, and we are able a posteriori to evaluate the curvature, which is 0 up to 10 minus 10. And if I want to impose the tetrahedral symmetries, so this is, excuse me. So So this is the surface. So you see some holes which are located on the edges of the tetrahedral symmetries, and some other holes, the other type of holes, which are located at the vertices of the tetrahedron. Okay. And yes, this is it. And now to finish,
You don't have the dodecahedral case?
Excuse me?
I was expecting the dodecahedral case.
I do not have it right now, but I can do it.
I'm sure.
But I do not show it because it's relatively close to the sphere, so it's a little bit it's less simple.
Too many holes.
Yes, you have too many holes, so the surface is close to it's closer to the sphere.
And you can have it with Genesis 1 or?
So you have to impose some conditions. So you cannot choose whatever group you want of symmetry with respect to the genus. You have to ensure some compatibility. So for the tetrahedral group, I do not know. I do not know. And finally, so I just wanted to show you some surface obtained maximizing eigenvalues of higher index. And so I don't know if it's expected, but you obtain surfaces, minimal surfaces with self-intersections. And that's it. And I thank you for your attention. And if you have questions.
It's not clear to me the role of the weight rho in all this, because it seems that you are somehow not considering it, or it's in your parametrization, because this is something you don't know. No, you have to.
Of course, it's an unknown.
But it's a function that you have to
Yes.
to optimize the eigenvalues. So where does it enter?
Okay, so you are right. I didn't tell you. So rho is discretized just by its Fourier series. So rho is a function, which is an unknown, which is supposed to be non-negative on every circle. Okay, I have one function on every circle. And so I discretized, we discretized rho by Fourier series. And so on each component of the boundary, exactly. And so it means that you will have one Fourier series by component. And then you use this analytic expression of the function, assembling the matrices, because yes, you are right, there is a rho in the eigenvalue problem, which is du dn equals sigma rho u.
And the fact that you have a pointwise constraint on rho.
The non-negativity?
Negativity, how do you?
That's a very nice question. We were lucky. We were lucky, and we forgot the constraints, and we didn't obtain a situation where it goes to zero. Sometimes, you know, sometimes the worst is not happening.
So if you want to go to the higher, so it seems that you need to have this nice space to obtain your
Yes.
precision. So if genus goes up, you use hyperbolic space as a model? Or?
So actually we worked on that during 6 years. So we tried a lot of things. We tried with pans, actually, in Poincaré disk. And the idea was that you can parameterize meromorphic functions on flat hyperbolic surfaces using the space of one forms. So you know, so the one forms are the space is of dimension 2j, the real dimension 2j. Okay. And so what we did is that we computed numerically this a basis of this space of one forms in a very, very accurate way, again by least square stuff. Okay, so it means that we had something like in Genius 2, we have something like 2 functions computed up to machine precision, and which are my 2 one forms. And with these one forms, composed by Riemann theta functions and its derivatives, it's very, very technical. You may recover a description of all these orders for meromorphic functions. So to answer your questions, we start with pans in the hyperbolic disk. And since 2 years ago, we are using a representation which is easier, which is Schottky representation. So we are using Schottky representation with doxodromies gluing together disks. This gives us one forms again, and based on these one forms, we apply exactly the same constructions that the one we used for pans, and we obtain the. Did I answer the questions? We can discuss a little bit further if you want.
Maybe I'll just quickly ask, in the last picture, do you impose any symmetries in it? How did it?
No. So the one with the sigma 2 or sigma 3. So this one, you mean? So this one, there is no symmetry imposed.
But is it supposed to be the maximizer, or you don't know for sure? Because it's weird. I mean, it's in B3, right? And you.
Yes. So it's the maximizer of sigma, let's say sigma 2, I do not remember. So it's the maximizer, the local maximizer.
The local maximizer.
Yeah, but once you have a local maximizer, you have a minimal surface in the bore. Huh? You do not need to be a global one. Huh?
No, you don't even need to be a maximizer.
You just need to be a critical, exactly.
Yeah. But this is a local maximizer. The claim is that this is local.
This is a local maximizer, yeah, for sigma 2. If I remember, sigma 2 or sigma 3, let's say.
How many boundary conditions, boundary components do you have here? 1? It's not easy to.
No, it's not easy. So 2, I think. And it's lambda 3. Lambda is equal to sigma.
And but you don't know if it's a global maximum.
No, for sure we do not know that. Let me say that we investigating these geometrical objects, starting from different configuration, we didn't obtain very different results. For instance, we were very attracted, perhaps Waxton told you, we loved the one boundary component generous one case, which is a crazy surface. This is a wonderful surface. And our idea was, is it possible to parameterize this object analytically, really analytically? Is it possible, if we have the right basis, is it possible to say, okay, take square root of 2, Weierstrass, blah, 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 and obtain the exact parametrization a posteriori? So I forgot what I wanted to say. So at the end, no, I forgot. What was the question? I'm sorry. You do not know neither. So fine. Our local or maximum, yeah. And so thank you. So in the Genius 1 case, one boundary component, we always obtain that one. So for me, I suspect there is no so many others.
You mean optimizing the first eigenvalue?
Yes, but
even without, but you said there's one in B4. Yeah. There's something
with one boundary component. Huh? With one boundary component.
Can you imagine to cook up a computer-assisted proof for your?
So
surfaces?
No, I mean at the end, our objective was really naive. It was to obtain an expression to consider the natural basis and hope that almost all the coefficients were equal to 0, and then we prove that it is the right parameterization. That was so you see, it's very modest. So now to prove that the computation provide, so what do you mean by a proof? We can provide, I think, so what we can do is to estimate precisely the mean curvature.
By computer-assisted proof, I mean some estimate relying on interval arithmetics that say that there is a true local maximizer.
In that range, in the range of some coefficients, because at the end, essentially at the end, I have a parameterization which is of that type. This is very naive. Okay, and the unknowns are here. Okay, and so what I can do, but this is relatively simple. It just depends on the derivative of these guys, is to say that in an interval associated to the AI, a small one, I have a true surface. I think I can do that. Yes, I think I can. So this is true for the mean curvature. Let me think about. No, this. So then you will have to play with. You will have to play with the two conditions. I mean, to be orthogonal to the sphere, in the sphere, the three conditions, and mean curvature. So it means it's not only mean curvature. You see. So what I want to say is the fact that I will have an interval for every of these conditions, and to have them together is not clear to me. I'm not sure I can provide an interval. That's the answer. But I'm sure that I will provide good quality approximation. Yes, Jean.
So you looked at the optimization of, say, the first eigenvalue to get minimal surfaces in the last few years. There was also other similar functionals, like say weighted sum of the first three eigenvalues, something that provide minimal surfaces in ellipsoids, for example,
yes.
or the recent other paper by Fraser and Chain where it's in products of balls. In particular, you can get minimal surfaces in a cube or a cylinder, for example. Have you investigated these as well? Because in a way, especially the one in ellipsoids might be slightly more stable, in fact. Because you don't have multiplicity
Okay.
issue.
Yes, which is one of the main difficulties. So we really thought that we will have the possibility to be more clever than people from geometry, because we have a huge range of possibility to investigate functionals and at the end we were not able to provide a functional which is adapted even to any ellipsoid. I mean, we have functional for some. There is theoretical article.
I mean, there's this paper by Romain Petridas, right?
But it's for specific ellipsoids.
Yeah. Well, I mean, for any ellipsoid, I can give you the functional that would reach that ellipsoid, right? It's
No.
I thought that
For functional, there exists an ellipse.
for functional there is an ellipsoid. It's
Yeah.
not. You can't prescribe the.
I think you cannot.
Implicit.
Yeah, I mean, I thought the ellipsoid was a function of the coefficients that you had in the.
So yes, so the answer to the question is that we were not able, but that we really think to it, and we even think to change the eigenvalue problem, change something, consider other eigenvalue or other functionals, but we are not able to plug it, because there is an interplay between all the boundary conditions, all the optimality conditions, and it's not simple. So first we always used a gradient flow, and then to obtain very precise solution, we consider, so as you know, so when you guess the multiplicity, so very quickly you will see when you do some optimization, you will see that the multiplicity is 2, 3, 4, whatever. So when you know the multiplicity, and you are very close from the optimal point, then it is very, so there is an adaptation of an Overton article which suggests to work on the smooth manifold, which is the space of matrices of given multiplicity. And then in this space, you optimize the mean, for instance. But there is a trick, because you have to be able to project on that space. And so we use, locally, we use an SQP. I don't know if you are sequential quadratic programming description of the function, of the functional, in order to maximize the functional, imposing the constraint of the multiplicity, okay, in order to be smooth. And then we have algorithm over the two, and then we can obtain very precise results. But it's a combination of first gradient, then SQP, but the implicit description of the manifold of matrices of fixed multiplicity is a little bit tricky. Because you have to scale the eigenspace. No. It's something like 1 or 2 hours. But it's in several steps. I mean, yeah, it's not a machinery which is perfect. You have to double check every step.
No more questions? Let's take it on.